Well, welcome back. We're in Vectors and Projectiles doing the exemplars here. Exemplar number 1 specifically. Jamie Pierre skis off a cliff to set a new world record in Grand Targhee, Wyoming. I've actually mountain biked on Grand Targhee Mountain in Wyoming. Anyways, you can pause this and watch that link there of a interesting video of him doing that kind of skiing, more falling with style, as Buzz Lightyear would say. All right, but let's get into the physics here. First, I'm going to draw a picture of what's going on. You should draw a picture there too. So I have a cliff. I'll make it kind of big here so I can actually see things. And he's way up on that cliff. Now, I usually draw like idealized situations, so I recognize the cliff wasn't perfectly flat on the top, but makes it, we're doing this just so we can understand and see things. He's got little poles there. I don't know, does he have poles in there? I gotta watch that video again. And a little helmet here. Okay. So he's gonna ski off. I'm gonna draw his path there. He basically just like falls. Well, no, he is skiing horizontally there, so he's not basically falling forward. He's going to go out some and then, make some sort of arc. Now, it's a pretty steep arc in the video there. And so this is like slightly exaggerated how much he's arcing out there, you might say. He was skiing 8 meters per second east or horizontally east in my picture here. So I'm going to put my original velocity as 8 meters per second. I like labeling things that I know on my diagram here. The cliff was 255 feet high or 78 meters. 78 meters is the SI, or are the SI units for displacement. I recognize that's a displacement and I'm going to label it as delta y straight away. So now when I go back and I try to do problems, I go, hey, yeah, I already have that delta y. It's right there. I already identified that as being y. When he landed at the bottom, how much time will have elapsed? So I should probably put all these in different colors here. T is a big question mark. I don't know how. And then how far he landed. Well, that's a displacement in the horizontal direction. So that's like the x dimension there. And as always, we assume that we're following the Cartesian coordinate plane as we know and love, unless we say otherwise. So I'll list it specifically. We know that's the positive side and positive side over there. Negative side here, negative side there. Now, you don't really need to list that unless you're doing something other than the normal Cartesian coordinate plane, which you can do anytime as well. Okay, so how far from the cliff will you land and how fast will he be going? All right, well, thus far, we recognize that the x dimension motion is totally separate from the y dimension motion. So here's my x, so I'm going to make columns here. Here's my column for everything that's going in the x dimension there. Here's my column for everything that's going in the y dimension. And notice that I'm not going to mix these things up here, as the x bits are separate than the y bits. So, well, what do I know? Well, I'm trying to figure out delta x here, and I'll write down equations that are useful. Like delta x I know is 1/2 at squared plus v naught t. And I know that's true anytime I have constant acceleration. So notice that this is in the x dimension. So now I'm asking myself, oh, let's go through these values. Hey, do I know what the acceleration is? Well, now careful with that one, because this is the acceleration in the x dimension. So now I think about this, and yeah, I could even plot this out. You know that what's pulling it down, you'd say gravity's pulling that down. Yeah, okay, cool. How am I going to label that? Well, things that are pushes or pulls, we actually call a force, and sub g for gravity there. We're going to get into all the details of that next unit. But for right now, we know that gravity's pulling it down, great, and we know that that causes, because we saw that in the last unit, that causes an acceleration due to gravity, which we appropriately just shorten as lowercase g, and we know that to be 9.8 meters per second squared. Okay, cool. So I'm listing things that I know. I know that something's pulling it down, force of gravity, and it's accelerating down. Now, is there anything else pushing or pulling on it? And generally, for all these projectile problems, no. Now, we're starting projectile problems just after the projectile, which is the person in this case, stops touching something like the top of the cliff there, and then we end the problem just before it interacts with anything else. So the instant it touches the ground, or the instant before it touches the ground, a lot of people will say. Okay, so just when it's like quote unquote in flight is when it's a projectile here. Now you might say, well, isn't it like interacting with air? And remember that a big key thing here is that we're not gonna do any calculations on air resistance. So we are ignoring all air resistance. So we're gonna say, hey, we're gonna do this, but like there is no air that they're interacting with. And the reason for that, again, is that air resistance calculations are very complex. And next year in AP Physics, we'll touch maybe just the surface of air resistance calculations, and then that's it. They are very complex. So we're going to do things without it, and from time to time, we'll talk about it as if, oh, what if we put in air resistance? How would that change things? And we'll just talk about it. We won't do any calculations with it. Okay, so back to acceleration. What is the acceleration? Now remember, we're working in the x dimension here. And so the acceleration, well, what we listed before was going vertically, up and down. What's the acceleration horizontally? Well, to get this acceleration, I had to put some force on it, the force of gravity, and it gave me this acceleration. Well, in the horizontal dimension, I don't have it touching air. He doesn't have a rocket on him. There doesn't seem to be anything pushing him to the right, nor pushing him to the left, again, after he leaves that cliff there. So that means that the acceleration is going to be 0 in the x dimension. And so sometimes I label a sub x, and to remind myself that this is in the x dimension. However, it should be apparent because, well, we have a header up here that says it's the x dimension. So that guy is 0. Furthermore, do I know the original velocity? Again, that's the original velocity in the x dimension. And we said that it's going 8 meters per second to the right, and so I know that this is a positive 8 meters per second because it's positive in the positive x direction there. All right, so now we can simplify this equation here a little bit, which is nice. I can figure out my displacement in the x direction, which is one of the things we're trying to figure out, by going half times 0 times t squared. Well, that's just 0, so I can leave out that term there. And so now I'm going to have v naught t, and I'll put in the 8 here. I like to keep it as variables first. And so that's going to be 8 times some t there is my delta x. Now, how long is it going to be in the air for? Well, I don't know. That was one of the things that we're trying to look for there. We're trying to figure out what the time is. Okay, so right now, I can't solve this equation. I need a time. So, well, I have two options. One, I could go, this is impossible, and I can't do this because I found something I can't solve right now. Or I can go, wait, hold on. I have this whole dimension over here, this y dimension over here. Maybe I could do something in there, and maybe that something will help me figure out, in this case, the time, maybe something else as well. Okay, maybe it'll unstick me. Maybe I'll get unstuck. Okay, so what could we do in the y dimension? Well, what do I know in the y dimension? I know delta y, and I know the acceleration as we just went through. Okay, so let's write down an equation that might be useful. That displacement equation, in this case delta y, because we're going in the vertical dimension here, same ideas though, is equal to 1/2 at squared plus v naught t. Now remember that all of these things refer to the y dimension, and that's why I put this column here, just to remind myself. Let's go through and let's think about, do we know these values here? So let's list them out. Well, this one we know, that's going to be 78. Now that is 78 is the height of the cliff there, but now well, hold on a second. Let's look at that though, because that's a delta y. So what's my change in y? Okay, my change in y is you're going from something high, 78, down to something low, like you might even say maybe down here is 0. Reasonable if you said that, and it's like the ground. So now what's his change in the y position? Well, remember, the change in y position is delta y, or delta anything, is just the ending bit minus the beginning bit. Okay, cool. Let's try and do that, and kind of off to the side here. Well, the ending position, look at the picture here. The ending position is 0. The beginning position was positive 78. So now my ending, y, is 0. My beginning was 78 meters, and so my delta y is not a positive 78, it's a negative 78. What does the negative mean? It means that he was going downwards. Check it out. He's going towards the negative values of your y position. Think about that. If you plotted that on this Cartesian coordinate plane, it would start up here, and then he would go going down there. And so you'd be decreasing in y values. Yeah, and that's what he's doing. So that's why the delta y is negative 78. Okay, cool. So we know that value. That's good. What about acceleration? Do I know that? Yeah, we just said that before, that the acceleration is g 9.8. Now I need to put a unit with that, so let me go ahead and let's put in that my acceleration in the y dimension. You don't have to do that because you're in this y column here, but sometimes I do for clarity's sake. We got to put the direction with that, and that's going downwards. That's the negative direction, and that's in meters per second squared. Great. What about the beginning velocity? Do we know that? Well, yeah, I mean, it told us that it was going 8 meters per second at the beginning, but now check that out, because that's a beginning velocity, v naught, but in which direction? That's in the y direction. So then you got to ask yourself, well, how fast was it going up and down at the beginning? Right, the instant he came off of that cliff, how fast was he going up and down? And you'd say, well, it was a horizontal cliff. He went off horizontally. And so he wasn't moving up or down. That's right, V naught, you might even say sub y. Look, we got sub there. Sometimes you'll see that, and I'll do that from time to time too. He wasn't moving up or down, so that's 0 meters per second. Oh, okay, cool. Now, probably didn't realize all this at the beginning. That's okay. So let's go put that in. Well, the ending bit is 0 times any t. That's just 0. So let me rewrite this in with variables here. Delta y is 1/2 at squared. And now let me put in all of the blue bits that we already knew. We knew negative 78 is equal to 1/2 the acceleration. Remember, that's negative 9.8 because it's accelerating down. It's the acceleration vector, as you can see, is pointing down. And then multiplied by t squared. I don't know what t is, but that's okay. Check that out, because I only have one variable there, and so I can solve for that. So I'm going to back up here and I'm going to do this. I'm going to do this with variables. So I showed you that you can do this. Now I'm going to go and solve this with variables. So I'm going to move the 2 over to the other side. So I'll do 2 delta y, and then divide by my a, and then take the square root of all that. And so now I get t by itself. Hopefully I didn't do too many steps there at once there for you. Just multiplied by 2, divided by a, took the square root of both sides. So now I can go t is equal to all of this bit. And this is usually a more efficient way and usually an easier way. Usually you make less mistakes this way if you rearrange it with variables and then you put in the stuff. So that's 2 times negative 78 divided by negative 9.8. Now we look at the math here, the negatives work out, that becomes positive, which is nice, because we can only take the square root of a positive number and get a real number, and I expect my time to be a real number, because every time that I've ever operated a stopwatch or a clock, I've always gotten real times. I've never gotten an imaginary number yet. Maybe one day, or maybe if you shrunk down to the size of an atom, or an electron, maybe then there's like imaginary times. Yeah, quantum mechanics, you say? Interesting. Okay, anyways, we pick up this calculator here, and we go and we take the square root of 2 times 78, and I'm just kind of doing it here, you're doing it too, divided by 9.8. I left out the negatives because they cancel out anyways. And I'm checking out my parentheses and making sure that I got the parentheses and such. It looks like I did. So I get 3.989, so I'm going to put 3.99 seconds. Now remember that I do not round this time. Okay, so I'm writing down 3.99 seconds, but on my calculator, I am keeping the full digits there. Actually, I can show you the calculator on this. Yes, I can. Yes, I can. Dunk. So I have a little calculator emulator here, and we can actually go through. And what did I just do? I just, since this is the first time you've probably seen all this stuff, let's go through that. We got 2 times, oh, and this is the newer version than what I'm actually using there on 78. And so it does some of this fractions there for you. Oh, no, I need to put it in the parentheses there. I'll go back and do that. Divided by 9.8. Now, will that actually do that properly? I think it actually will, because if you look at order of operations, it's going to do all the stuff underneath the square root first, because it's like in parentheses there. And so then it'll go left to right, since multiplication and division have the same order. So the tiebreaker for anything that ties for the same order is left to right. So I'll do 2 times 78 and then divide by 9.8. So it looks like it'll do that correctly. And it gives me the same answer as when I put in parentheses there as well. Now notice that I'm going to keep that, and I don't want to have to type that number in a whole bunch of times. So bottom left-hand corner, you see that STO button? Boom, STO, store. Now I can choose any letter that I want. Well, that was a time, so I go find that T there, press enter. Now I can use T. Now if I needed to do like, oh, for whatever reason, I needed to do 3 times that T there, well, I can do 3T, and boom, it multiplied that T by 3. And if I ever forget what T is actually stored as, I can just press enter and boom, there it is. Oh, that's neat. That'll save you tons of time, headache and frustration and da-da-da-da-da. So let's get back to this. So I store that time into my calculator there, and I extend my little column break there. And now I go, hey, that's the time that it takes to get down to the ground there, right? That's the time for him to fall and then hit the ground. Well, if that's the time, and I'll put that in there, 3.99, what's the time that it took to go horizontally? And you're saying, well, man, if I was standing by the side and I was timing this person doing this, it would be the same time for him falling vertically as him going horizontally. It's just one time value from when he left, became a projectile, to when he arrived at the ground, when he ended being a projectile. It's just one time value. Huh. Neat. That makes things real nice and easy, because now I found that time value and I can put that time value in up here. It's the same time. Cool. So while motion is separate between X and Y, there's only one time for the events that are happening here. So now I go and take that 8 and I multiply it by my T value as I have in my calculator there. And let's do 8T. Oh, maybe I should do that so you can see there. That becomes 31.92. I think you probably got it though. 31.92, and that's in meters there. Now, is it in meters? Let's go ahead and let's look at that. So I found out my delta X. That's kind of nice. That was one of the things that specifically asked for. I'm going to box that. I found the time. That was one thing that it specifically asked for. I'm going to box that. Now, does that actually come out to be meters? Let's go look at the units there, because that's kind of interesting. So I'm going to recopy this line down here. Delta X is equal to 8. Let's put in the units for the 8. The 8 was meters per second, as we wrote up there, meters per second. And now I'm going to multiply that by some time value, 3.99 seconds. What happens with the units? Well, units follow the exact same rules as numbers or variables do. The 3.99 isn't written as a fraction. Well, I'm going to rewrite both of these as fractions, because this is the first time we've done it. So I'm going to write this 8 as a fraction. Well, clearly it's just 8 over 1. That's easy. Well, what about the units? Well, that's 8 meters for every 1 second. Another way to say that. Okay, cool. And then multiply by this 3.99 as a fraction. Well, it's almost 4, but I'll keep it as 3.99 over 1. And the seconds are in the numerator there. As we see, the seconds are in the numerator. Notice the seconds in the denominator. So I put the other seconds in the denominator. Now, when I look at this, I go, hey, what happens to the units? Well, I'm multiplying fractions. Remember, when you multiply fractions, you go straight across. Straight across. Do not cross multiply. Anyways, when we multiply straight across there, I recognize that I have a seconds in the denominator and a seconds in the numerator, so they cancel out, and I am just left with meters there. So I do get 31.92 meters. And that's my delta X. So now we go back and we look and make sure that we've actually got everything, that we actually solved for everything. So we go back up to the top here, and let's read here how much time will be elapsed when he lands at the bottom there. And we did get that. That was the 5.99 right there. Okay, it was 3.99, sorry. So we got that one. How far from the cliff will he land? That's our delta X, and we got that 31.92. But how fast will he be going? We haven't answered that yet. Forgot about that. Oh, man. Let's go and do that. Okay, so how fast is he going to be going? Well, let's think about that now. He's moving to the right at the beginning, and then as he goes along here, nothing's speeding him up or slowing him down in the horizontal dimension. But, so that should be constant in the horizontal dimension. As we talked about before, the acceleration in the horizontal dimension is constant. Or is 0, and therefore the velocity is constant. But in the vertical direction, that thing is speeding up, as we talked about here, from the acceleration due to gravity. And so then in the vertical direction, it's getting faster. So now that sounds like a vector addition problem here, because it sounds like at the end, if I was going to draw his velocity here, at the end, we know that he's going to be moving the same original v naught x, you might say, 8 meters per second to the right, because nothing was speeding up or slowing him down there. However, now he's going to be also he's going to also have some velocity in the y direction there. I don't know what that is. Let's see if we can go figure that out. So I'm going to go work in the y dimension here, since I need to figure out that y bit. I'm going to make another little break here just so I don't confuse that with the previous calculation. And I go and I look at, I have two equations basically, and I look at the other one, and that one has velocity in it. So now we're in the y dimension, so you could think about it as there's a little subscript y's on both of these, but we're in the y column here, so we automatically assume that that's what we're working at. Put in the acceleration, again, that's in the y dimension there, so that's negative 9.8. My time, that's going to be the total time there, so that's going to be the same as right above there. And then plus my original velocity, well, that's in the y direction, and we said that was 0. So now I'm going to take this t value, let me get a different color here. I'm going to take this t value, and that goes right into there. And so I grab my calculator, and I do negative 9.8 times that time there. And remember, I don't use the 3.99, I use the whole string of values there. And then plus 0, so don't have to worry about that. And I get negative 39.0, well, it really rounds to 10 actually. 10 meters per second. We're not going to be worried this year about significant figures. Significant figures is the correct way to round. We'll just, round to something reasonable, like 2 decimal places. For numbers larger than 2 decimal places will work just fine. This is the velocity, not the total velocity, the velocity just in the y direction. You might ask, hey, why is it negative? Let's look back up here. We go, oh, I expected that this velocity here to be going downwards there. So yeah, it's negative because that was describing that it's moving downwards, that the velocity is pointed downwards. Okay, so now I need to add these vectors together. So let's go and let's do that. So add these vectors. I'm going to redraw it down here. And we had this 8 meters per second over there. And remember, I can move vectors around there, so I'm going to put the other one right here, and I'll list it as the positive. We already have the direction going down, so sometimes it's a little bit redundant to put the negative and when it's already a vector there pointing down. Usually, when you are drawing the vectors, usually just kind of list the magnitudes, the values of them, because the arrows give you the direction. And then my resultant vector is this one here. And that's going to be at some angle, and I'll label that theta. That's below the x-axis, you might say. Okay, so first, let's go get that. We're using Pythagorean theorem here of v is equal to the square root of the 2 legs of the triangle there. And so that's going to be 8 squared plus my 39.10. Again, don't round that value. That's the whole string of numbers that you have in your calculator there. And we're going to square those, add those together, and take the square root of that. So notice that the negative bit, whether you put the negative in there or not, doesn't matter. You're squaring it, so it's going to go away. So I have those values in my calculator, and now I'm just punching them in here. 8 squared is 64. Don't even need to do that one. B squared. I'm not doing that one in my head. And this is saying I get the exact same value. Is that true? Hold on. Did I just did I do my parentheses wrong here? Maybe. B squared. And, oh no, I don't get the same value. It's just slightly off. You gotta look closely there. You get 39.91 meters per second, and so it is different. And then you look at that and go, why is it only 0.81 different? Well, check out. Look at the relative sizes of 39 versus 8 there. So the 8 is going to change it, but not by a huge amount. So here's my total velocity. But then, like, which way is it pointing? Well, let's go ahead and let's do some math here. You can use sine, cosine, or tangent to find that angle measurement there. And we could use any one of them. I'm going to go ahead and use tangent because I have both of the the legs of the triangle listed there. So it's going to be tangent of theta is going to be equal to the opposite, which is the 39.10, divided by my 8. And again, we do inverse tangent on both sides there. And we're not using the rounded value of 39.8. We're using the whole value there. And so when I go and do that, let's grab our calculator. And this is, again, why I'm storing values. So like the 39.10, I store that whole value as a big string of numbers as, in this case, letter B here. And I get, and that's equal to theta. And now theta is equal to negative 78.45. 78.45. And that's degrees there. Okay, cool. So, and you might say, well, why is it negative? I expect it to be negative because notice that it's below the x-axis there, you could say. If you're not sure if something like that threw you off, well, let me erase that a little bit and extend my line over here, and you could always go and check that with sine, cosine, or tangent since we have these other values here as well. So let's go do that just to see what we get. So let's do the sine of theta, and that's going to be equal to my 39.10 over the hypotenuse there, which is the 39.91. I do inverse sine again, and I'm not going to write that one out. I'm assuming that you can do that one by now. And we go do that. I'm punching that into my calculator. UR2, stored values. I stored the other 39.91 as well. And boom, lo and behold, I get the exact same value, negative 78.45 degrees. Cool. Yeah. Now, did I... Okay, that's a good question. Did I put in the... No, that's not... That's okay. Okay. So, I'm gonna backtrack there. When I did this, notice how I wrote the positive 39, but in vector space, in mathematical vector space, these are actually negative 39 there. And when you do that, then you actually get the positive value here. So careful about that. Ultimately, what do you know? You know that the magnitude of that theta there is 78.45. Oh, sorry, I have the diagram right down here. And we can see that it is below the x-axis there. Okay, cool. So it does look like that. We can always add or take 360 minus the 78 and get that my, you might say, normal measurement of measuring the angle from going counterclockwise around there as we normally do. I'll label that as alpha there. And we just do 360 minus that 78 and we get 281.56 degrees. Either way that you report this is totally fine. Just make sure that if you do report this, actually I'm going to erase that. I'll talk a little bit more about that. When you do report this, notice that you can't report these both as a positive value, as the 78, you know, as theta is measured here, is actually a negative 78 there, and it is an actual negative 78 there. When you put in the negative sign for the angles here, remember that sine, cosine, and tangent don't always give you the correct signage there. You may remember from math class that sometimes you have to like check those signs for some of those in some of the particular quadrants, and that's true. And that's why I'm always taking these values and matching them back up to my diagram there. So anyways, even though the math does come out to be positive when you actually put in that negative as I did there, I kind of like forgot about that and just went barreling ahead there. Sorry about that. You do need to report which way that you're measuring that angle there from the clockwise or counterclockwise, the correct way in black there, or the standard way I should say in black, and the slightly non-standard way in blue there. So either way you report that, make sure that you do have direction. All right, that's how fast it's going and which direction it's going in. Now if we go back and reread all the questions there, I'm pretty sure we answered everything. All right, that's it. Have a beautiful day. See you. Bye.